Welcome to this informational video on how an oscilloscope probe will affect your measurement. This video will explain how the probe changes the signal you're measuring and what probing specifications to look for to minimize probing effects. You want to select a probe that meets the following criteria: faithfully transmit the signal from your device under test to the scope, and do no harm, meaning you want to select a product that changes the signal at the test point as little as possible. When you connect a probe to a circuit, it will change the signal you're measuring and can affect the operation of the circuit. The probe tip is conductive, so it's going to draw some current to produce a voltage on the oscilloscope. Because the probe tip has to draw current, it's going to load or harm your circuit. This video is going to focus on two probe specifications that are related to the probe harming or loading the circuit and what the negative effects of probing look like. These probe loading factors are input resistance and input capacitance. A probe's data sheet shows an input impedance specification made up of input resistance and input capacitance. Usually, the loading of greatest concern is caused by the capacitance at the probe tip, because as the measured signal's frequency increases, the capacitive reactance decreases, causing more probe loading. Let's first discuss the input resistance specification. Depending on the source resistance, the probe and scope input resistance will reduce the amplitude of the signal under test, as shown in the waveform on the top right. For most applications, the input resistance of a probe is less likely to cause significant probe loading, since most 10x passive probes that ship with an oscilloscope have 10 megohm input resistance. Using the example equation, you can see how the probe's large 10 megohm input resistance will have little impact on the measured signal. With 10 megohm, it's difficult to see the effects of input resistance at the DUT. Let's take a 200 ohm resistor and touch it down onto our device under test to simulate the probe plus scope input resistance. Before we do, just to describe our test setup, we're using a voltage source with 50 ohm source resistance, and you can clearly see that the DUT is connected to the input of channel 1. This is what's happening at the device under test. This is not the output of the probe. Taking my 200 ohm resistor and touching it down onto my device under test, you can clearly see the effects of input resistance. You will notice that my rise time value is still roughly the same. However, I have had amplitude loss as the signal has changed from 244 millivolts to about 220 millivolts. You also notice that the waveform shape is relatively similar as the source signal. One of the most critical probe specifications that is almost always overlooked is the input capacitance. Many times, users will focus on the 10 megohm input resistance specification, but the loading of greater concern is the capacitance at the probe tip. For low frequencies, this capacitance has a reactance that is very high, and the loading is not as much, similar to the effects of input resistance. But as frequency increases, the probe's input impedance goes down and the loading is much greater. You can see the effect of input impedance on the waveform on the right. The high frequency content at the front corner of the signal has been degraded, and important high frequency information is gone. Using the simple model above, a first order equation shows that a larger input capacitance will result in significantly slower rise time and lower bandwidth. Using the same test setup, we will simulate the effects of probe input capacitance using a variable capacitor soldered into our test point. We will adjust the capacitance from 7 to 50 puff to observe how probe input capacitance degrades the high frequency content. Again, you can clearly see the DUT is directly cabled to the oscilloscope, and this is not the output of a probe. Let's now adjust the variable capacitor to see how this additional capacitance affects the front edge, so we can see how a probe with a larger input capacitance specification will do greater harm or have more loading on the signal you want to measure. Adjusting the capacitor from 7 to 50 picofarads, you can clearly observe how the front edge rolls off and the rise time is considerably slower. We've seen how the probe affects the signal at the test point. What about at the probe output? To see the effects of probe loading at both the test point and at the probe output, we're going to use two oscilloscopes. The scope on the left will display the output of the probe. The scope on the right will display what is occurring at the device under test. Here's how a 1x probe with 100 puff input capacitance affects our source signal, which is a 244 millivolt step response with 420 picosecond rise time. The original signal has been degraded. The rise time is significantly slower and the amplitude is changed. Again, you have to ask yourself, what kind of harm is the probe doing at the test point? This is the signal that is going to travel through the cable to the probe's compensation box and ultimately to the scope. You can see further effects of the probe at the output. The bandwidth is insufficient and the signal is further rolled off and degraded. Clearly, this probe is not capable of making this measurement. Here is an example of a passive probe from Agilent that has 10 puff input capacitance. Again, you can see how the probe's input capacitance is affecting the signal you're trying to measure. The front corner of the signal contains all of the high-frequency signal content, but that information is being compromised by the probe. You can see how the front edge is rolled off. Once again, how does the probe harm the signal? The rise time has been degraded to 1.1 or 1.2 nanoseconds, and this is what is happening at the test point. The signal hasn't even started through the cable, the comp box, and to the oscilloscope. Here's the output of the probe, and the signal looks as you might expect. The waveform shape of this signal is similar to the original signal, which is shown as a reference. The rise time of this signal is somewhat slow at around 800 picoseconds, and the amplitude is favorably compared at around 246 millivolts. However, remember what the signal at the test point looked like? The probe had significantly loaded the signal under test. The front corner was degraded and the rise time was significantly slower. It looked very little like the original source signal. This degraded signal will be further changed as it travels through the cable to the output. This test signal has to be reconstructed by the probe and the scope to make it look like the original signal. This kind of loading or harm may have adverse effects when you're performing important circuit validation. A product that has redefined performance in the passive probe category is the Tektronix TPP 0500 with industry best input capacitance at just 3.9 puff. Touching the TPP 0500 down at the test point, you can clearly see the benefit of a probe with low input capacitance. The signal on channel 1, which is the loaded signal, is nearly identical to the source signal. Once again, you want to make measurements with a probe that is going to do less harm, meaning the probe is only going to minimally affect the signal you're measuring. A TPP 0500 offers nearly the probe loading benefits of an active probe. Let's once again view the Agilent probe loading effects and compare it against the loaded signal from the Tektronix TPP 0500. The differences are dramatic. In today's world, signals have faster edges and tighter margins, so the designer has to make the effort to model, run simulations, and validate the design. When you spend that much time and effort in the design process, you don't want to second-guess the measurement system or spend additional time troubleshooting due to measurement inaccuracy. In this case, one would have to question if the effects of probe loading are the weak link in validating your design. Here's an example where the probe's loading effect may not only cause measurement inaccuracy, but can also affect circuit operation. In this case, the probe's large input capacitance has caused the signal to fail to meet critical setup and hold time requirements. You can also see how a degraded front edge or ringing can cause reflections, which will compromise signal fidelity. When you're validating your design, the last thing you want to do is fight the test equipment. Make sure you choose a probe that is going to do less harm by selecting a probe with low input capacitance, such as the TPP 0500. When selecting a probe, users will often look at what are considered to be the banner specifications, which are bandwidth and dynamic range. As you've seen in this video, the probe's input capacitance is a critical specification. A probe with less input capacitance will do less harm or cause less loading on the test signal, which will offer measurements with greater accuracy. You can find quality probes with low capacitance at www.tektronix.com/probes.